Green's functions, you may not be able to find them so cleanly analytically in this case. But hopefully you got some clue on the homework that another way to find these Green's functions essentially is to use eigenfunction expansions. And so people will do that a lot of times. Even for irregular domains, you can oftentimes find nice approximations using these spectral methods, essentially. Okay, so done with Green's functions, at least in terms of lectures. I think we'll circle back with just some practice problems on Friday. In the last part of the course, I think maybe the last 4 lectures or so, or however many more I do, maybe 4 or 5 lectures. I want to move to nonlinear equations, and in particular, talk about a special kind of solution that has certainly been a research strength of this department, but also it's a convenient formalism for kind of getting some explicit solutions, and comes up on a lot in continuum mechanics, mathematical physics, traveling wave solutions, okay? Also mathematical biology, okay? So we looked some at wave propagation for quasi-linear equations in the case of method of characteristics. And what we found, right, way back, remember when we did method of characteristics, okay, is that we essentially reduced PDE to systems of ODE, right? In general, you're not going to find a nice catch-all method for solving nonlinear PDE, and so you have to take an approach like this where you can chop the dimensionality of equations down, so that it's manageable by some dynamical systems methods, or just methods from ODE. Okay. So the idea here is, if we suspect traveling wave solutions, what's the approach is essentially, borrow the idea of characteristics, okay, to try and reduce the dimensionality of the PD, okay? And the idea here is, usually you're not going to solve for the full evolution of some initial value problem for a nonlinear PDE. What you're going to find is a solution that your PDE could relax to over time. Okay, so another way to think of this is maybe as sort of finding a steady state of your problem, except that steady state is a traveling wave, so it's still gonna change in space and time. Okay, but it's going to change in a way that's much lower dimensional than solving the full spatiotemporal partial differential equation. Okay, so the approach then is to look for solutions, okay, along the simple characteristic psi is equal to x minus ct, right? Our simple characteristic that we first wrote down for the transport equation. And naive as this may seem, you may find it remarkable that this works a lot. I mean, especially if PDEs have been constructed to give you traveling wave solutions. Okay. So how does this work? Okay. Well, essentially, you take some nonlinear PDE, right? Usually it's going to look like this. du dt equals some big nonlinear function of u sub x, u sub xx. You could have, up to 4, 6 derivatives in space of some big nonlinear function, okay? And essentially you're going to assume that u of xt is of the form v of xi, where v is x minus ct, okay? So this means that instead of looking for a 2-dimensional solution in space and time, you look for a 1-dimensional solution along this characteristic, okay? Now, what does that do? Well, if we look at du dt in that case, what that means is that we have d dt of v of x minus ct now, okay? So that's going to be equal to d psi dt, and then v prime of psi, which is equal to minus c v prime of psi, okay? And so this means that we have the following ODE. We just have an ODE that looks like minus c v prime of psi is equal to f of v prime, v prime prime, etc. Okay. So this ODE, right, is often going to be a nonlinear ODE, okay? But an ODE is way easier to, deal with, and there are way more possibilities for analyzing them than PDEs, right? One of these is what's called phase plane analysis, okay? Where essentially we graphically represent the solutions to our equation. If this is just a second order ODE, we're in luck because we can write, a second order ODE just as a system of 2 first order ODEs, okay? And we have all sorts of, null-Klein, local stability analysis, that kind of thing that we can leverage. Some more classical approaches are like what's called a shooting method, essentially where you start at one boundary and you shoot solutions from minus infinity up to plus infinity, and hope to essentially get the boundary conditions to match up, okay? And we may also be able to directly solve, okay? And what is the point of this? The point of this is to see if and when the boundary value problem for v of psi, okay, which is going to involve some conditions at the free boundaries, right? V of psi has solutions, okay? And usually, right, you take something like this, right? Or you may take something like the first derivative, right, of v, okay? And that just assures that you have a bounded solution, either that tends to 0 or does not sort of just continue wildly oscillating as you go off to psi goes to positive and negative infinity, okay? So this is the setup. Let's start on the case of the Burger's equation, okay? No questions so far? All right. Trying to take it slow. All right, so let's look at Berger's equation, and in particular, we're going to take the viscous example, okay? Now let's remember back to inviscid Berger's equation. In that case, we had something like this, right? And maybe you remember that if you start off with like a ramp, something like this, right? And what'll happen is this will get steeper and steeper, right? Until we have like a shock right here at t equals t star, okay? And then we need to use distributional solutions here, okay? Well, that's a real pain for numerical methods, okay? It's also not really something that happens a lot in real life. It's just a function of this being an idealized model, okay? So adding viscosity essentially sidesteps these shock solutions, and it's actually a case that you can still analyze quite cleanly, okay? So what's that look like? Viscosity just means that you add a little bit of diffusion to your PDE. And this is not just a technique that people use for Berger's equation, but for many different PDEs where you may get some sort of sharp corners in your solution. Adding a little bit of diffusion, okay, is not going to change the solution that much, but it's going to make it much more numerically convenient to handle, even maybe more analytically tractable in some cases, okay? So I want that diffusion coefficient to be positive, right? And epsilon, you know, we're sort of assuming epsilon small, but it doesn't have to be small, okay? And it's also can be thought of as physical, right? So you could you essentially just have some nonlinear transport plus some dissipation of your concentration of media, whatever it is, okay? And so what are we going to do? Well, in the case of Berger's equation, we know that we had traveling wave solutions. Essentially, what's going on here is this is bending, 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 and eventually becoming a shock. But thereafter, if you apply the Rankine-Kouchner condition, you can show that this shock solution is going to propagate at a common speed indefinitely, right? So we don't think that, you know, every single solution to inviscid Berger's equation is a traveling wave solution, but we think that essentially the solution will eventually get relaxed to the shape of a traveling wave solution, and that will be sort of the main solution that you eventually evolve to over time, okay? So we suspect, right, a traveling wave solution, okay? And therefore consider the following onsets, right? So u of xt is equal to, and I'm gonna get a little bit different than the simple example that I gave up front, okay? X minus st here divided by epsilon, okay? So dividing by the epsilon, where does this come from? Okay, well, if you work through this, essentially you see that as you change epsilon, basically the steepness of your solution changes, so this sort of reflects that. Okay, you don't have to put it in there, but it cleans up the epsilons nicely by including it. So this whole thing is now what I'm calling my characteristic xi. Okay, most of our examples will just use an onsets like the numerator here, but scaling by the by epsilon helps in this case. Okay. The next thing I want to do is think about what kind of traveling wave solution should I expect to have, right? So traveling wave solutions, right? They can be pulses, okay, or fronts, okay? But here we expect a front, okay? What do I mean by all this, right? Well, a pulse is, or sometimes it's called like a soliton or something like this, right? Would be like where you have just a little bump of activity or concentration, and it, propagates at some speed, and it's the same shape always, right? So we will look at some PDEs that do this, okay? But this doesn't happen here, okay? If you start off with a pulse, it's gonna flatten out in the case of Berger's equation, okay? Or you'll evolve to something like a front, okay? A front is like a weather front or something like that. It's a wall of media or material or whatever the concentration of substances that you're modeling, right? And it's going to look like this, right? This is a front solution, and it's going to move forward like this, okay? This is like a forward moving front. You could also have like a receding front, right? Yeah. This is like a tidal wave or something, like, coming towards the beach, right? This is, I don't know, I guess, yeah, water sort of pulling away from the coastline or whatever. Okay. So, so depending on this, right, you're going to have a different convention for your left and right boundary conditions. You're going to have potentially different signs for your speed in this case. Sorry, I know we're using S for speed in this case. But that also has a sign. So technically, I guess it's your velocity in 1D. Okay.
Can a front just be considered a composition of pulses?
Well, it would have to be infinite, right? Because you'd have to add them all up, all the way back to negative infinity, right? So yeah, maybe you could construct things in that way, but I think it's kind of a fundamentally different solution, right? You can also have trains of pulses, right? So you could have, one pulse followed by another, followed by another, right? And the pulses can interact, all sorts of things can happen in nonlinear wave equations. So yeah, you look at some of the stuff that the two Marks in our department do, and then also Harvey Seeger has worked on these sorts of things. You get all sorts of interesting behaviors. We're just going to really touch the tip of the iceberg here. Okay.
So we're basically just differentiating between compact support and non-compact support.
Yeah, right. So yeah, pulses would have compact support, right? Well, but
we're just going to 0 at infinity.
Yeah, so it's not, you expect none of these to have compact support, right? It's
okay.
I'm just differentiating between, usually this you expect to, right, limit to some positive or negative non-zero value. It's about the limits, I guess. The limits of this are going to be 0 and 0. And then the limits of this are going to be 0 and, some non-zero number. Okay. So that's what we're setting up. Okay. Let's see that I'm almost out of time, but that's fine. Okay. So the idea then is that we're going to assume front solutions, okay? And the front solutions can either look like this, where this is, I'll call this V minus and V plus, okay? Or they could look like this, V minus and V plus, okay? And so then they could either be forward moving or receding in this case, okay? And so the idea is that at the boundaries, we can actually implement 4 different boundary conditions. It's not really a boundary, it's sort of the limiting behavior of positive and negative infinity. But essentially the limit as psi goes to plus or minus infinity, v of psi is equal to v plus or minus, and the limit as psi goes to plus or minus infinity of v prime of psi is equal to 0 in this case, okay? Now, I know we're out of time essentially, but let me say something. And this comes up sometime when we talk about assuming rotationally symmetric solutions. Why can you just do this, right? Why can you just assume that, oh well, this is the form of my solution, and I'm going to see